For this lesson, we're going to take a look at the graphs of rational functions. And in order to do that, the place we're going to start with what's known as the reciprocal function, which is just your basic 1 over x. As you can see in the two sample graphs, or the graph templates I have below here, I have two reciprocal functions. And so that's each of those is the parent, which is 1 over x. And so the first thing we're going to do is to refresh our memories on what do the changes to these denominators. So basically changing 1 over x into 1 over x plus 3 or 1 over x minus 1. What effect does that have on this graph? And if we remember those in terms of transformations, this one, 1 over x plus 3, that one would be a horizontal shift. And the plus 3 actually means it's going to have shifted to the left by 3. Now, what's the effect of a horizontal shift left by 3? It means all of the points on this graph have shifted left by 3. And very importantly, and probably most importantly, this vertical asymptote has shifted to the left by 3. So there is now a vertical asymptote there. Just going to try to clean that up a bit. And this key point, for example, this key point at 1, 1 has moved over here. It's shifted to the left by 3. And this key point at -1, -1 has shifted to the left by 3. The horizontal asymptote actually hasn't changed. The horizontal asymptote is still the x-axis. And at this point, when I teach this reciprocal function, I mentioned that we don't need to do a lot of points here. Once we get that one key point, then we can just do our best to follow the line of the asymptote to get the overall shape of the graph. So there we have a shifted left by 3. This second example for B, this transformation would be a horizontal shift. This one's going to be right by 1. And in this case, that means that the vertical asymptote has shifted to the right by 1. So the vertical asymptote is there. The horizontal asymptote has not changed. Then we have the key point here, 1, 1 has shifted over. It's now at 2, 1. And -1, -1 has shifted over to 0, -1. And just as we had before, I'm now just going to sketch in the rest. I'm not going to try to come up with any other points. You could. They're there. It's just, we're really just trying to get an idea of the overall shape. So, as I say down here, remember the zeros in the denominator, those are going to result in vertical asymptotes. Now, let's go on to our next example. What's the next thing we want to consider? What happens when a factor in the denominator is also a factor of the numerator? So in other words, you're going to be able to divide out factors between the numerator and denominator. This is something I've talked about algebraically, which is this notion of a whole, and I've sketched that out in classes and even I would expect in previous video lessons, but we're going to take care now of what does that look like. So if the factor in the denominator does not divide out, we get a vertical asymptote. If the factor in the denominator does divide out, we end up with a whole. So let's take a look at this one. It says to simplify the equation of each function and decide whether or not you have a whole or a vertical asymptote or both, and then sketch the graph of the function. So this first one, first thing you're always going to look for are common factors. So you're going to need to put this into a factored form to be able to do anything meaningful with it. A factored form is going to let you simplify it by dividing out terms. A factored form is going to let you identify the values of any asymptotes. So factored form is the way you want to go here. That numerator is not factorable. 3x minus 1 is already in its simplest form. This denominator, we're going to factor that by decomposition. The shortcut to decomposition is to break up these terms into 3 times negative 2 is what they have to multiply into. 5 is what they have to add into. What are two numbers that multiply to negative 6 and add to positive 5? And that's going to be positive 6 and negative 1. And then the shortcut that we use here is we take the leading value, the a value, and we put that underneath each of my numbers. Now this one, 6 over 3, we actually are going to simplify that into 2 over 1. And we put our x with the denominator. So we put our x with the denominator. So I end up with the factors x plus 2 and 3x minus 1. And as you can see, what's happened here is that I've got now, I think that's my highlighter, 3x minus 1 and 3x minus 1 are going to actually divide out with each other. And so I end up with a final simplified expression of 1 over x plus 2. Now, if I had started with that, just like up here, we did a 1 over x plus 3. So if I started with 1 over x plus 2, you should already have a pretty good idea of what that's going to look like as a graph. So what does the graph of 1 over x plus 2 look like? You might want to think about that for a moment. And then the other thing I need to remember are my restrictions. Now there's a restriction right here. X plus 2 is in the denominator. That means that x plus 2, we're worried about when does x plus 2 equal to 0. And you can see that that occurs when x is equal to negative 2. So one of my restrictions then, it's just written slightly differently, is that x is not equal to negative 2. And then I also have another restriction which occurs when 3x minus 1 is equal to 0, which is 3x is equal to 1, or x is equal to 1/3. And so I get a second restriction here, which is x is not allowed to be equal to 1/3. The restriction x equals negative 2, x is not equal to negative 2 is still visible in the final simplified expression. That means that x not equal to negative 2 is a vertical asymptote. And if we think about that in terms of transformations, 1 over x plus 2, the vertical asymptote that used to be along the y-axis has shifted to the left by 2, which puts the vertical asymptote at x equals negative 2, which is exactly the same as what we got from this restriction. So this restriction gives me x is not allowed to be negative 2. There's my vertical asymptote. Let's go ahead and graph this. So 1 over x plus 2, that's going to have a key point here. And another way to think about it is the key point, so long as we don't have any stretches or reflections, those two key points are going to be one diagonal unit from where the asymptotes cross each other. And so there's one of my key points. Here's another one of my key points. I'm just going to sketch in respecting the asymptotes. And now we're going to take it a step further than we have in classes, where we've just talked about that there would be a hole where x is, in this case, where x is equal to 1/3. So, well, where is that hole specifically? And the way that we find the hole, let's pick another color here to work with, orange. Give myself a little bit more room. I think I'll do it over here. So there is a hole when x is equal to 1/3. So what I do is actually sub into the simplified expression, which is 1 over x plus 2. And so that's 1 over, and my x value, I'm going to put a third there, plus 2, equals 1 over. Now, what is 1/3 plus 2? Well, that's 1/3 plus, and then with a common denominator, 2 is the same as 6/3. So we end up with, I'm going to get a little cramp for space here, I end up with 1 over 7/3, which is the same as 3 over 7. And so that tells us that there is a hole at an x coordinate of a third and a y coordinate of 3 over 7. Now I can't graph that very accurately. I can't graph 1/3 or 3/7 using this scale, but I can see that 1/3 is about there. And so that would mean I would finish off by putting an open circle there to indicate that that's where my hole is. And I might even label that. So that's at 1/3, 3/7. So that's how you would represent this original rational function. It looks just like 1 over x plus 2, but it has the additional graphical feature of having a hole at 1/3 and 3/7. Okay, so let's move on to this next one. Y equals x squared minus 1 over x plus 1. That's pretty easy to factor. X squared minus 1 is the same as x minus 1 times x plus 1. It's a difference of squares over x plus 1. X plus 1 divides out with x plus 1. So that means that its final form is x minus 1. There are no restrictions visible in this form, which means there are no vertical asymptotes. There is a restriction, however, from what we divided out here. So there is a restriction here that x is not allowed to be equal to -1. So what does this part look like? This is just a straight line. So what is the straight line y equals x minus 1? Well, that has a y-intercept at -1. It has a slope of 1. So over 1, up 1, over 1, up 1. Or we could go down 1, left 1, down 1, left 1. And if I join those with a smooth line, I get something that looks like that. Arrows to show that it continues indefinitely. But there's one other thing I have to add in here, which is that I've got a hole at -1. So when x equals -1, there's a hole in this graph. Now we don't even have to do the calculation. We can actually see the coordinates of that hole are -1 and -2, just because this graph was such a simple graph. But if I wanted to calculate it, so if I said I've got my hole at x equals -1, then we would go y equals x minus 1 equals, and we would just sub in that -1. And we, of course, end up with a y coordinate of -2, which is where that hole is now. For the next one, y is equal to x plus 1 over x squared minus 1. So basically the same factoring exercise, x minus 1 times x plus 1. The difference is that's now in the denominator, which means when I divide out those common factors of x plus 1 over x plus 1, that just is equal to 1. My final form ends up being 1 over x minus 1. In this case, we have the factor x minus 1 is still visible in the denominator, and that means that x is not allowed to be equal to 1. That is a vertical asymptote. And then the thing that went missing is that x is not allowed to be -1, and that, because that is now missing from the final expression, that's a hole. So this factor, which got divided out, turned into the whole. Now, the vertical asymptote is at 1. So that's going to be here. The graph of 1 over x minus 1, that's just shifted to the right by 1. So there's going to be a key point here and a key point here. I'm just going to sketch in my graph. Didn't do a very good job. Let me just repeat that left side if I can. Not great, it'll do. And then I have a hole at -1. So just like I did before, so I've got a hole at x equals -1. So my y value occurs at 1 over x minus 1, which is 1 over -1 minus 1, which is 1 over -2, or we would normally write that as -1 over 2. So at x equals -1, there's a hole, and the coordinates of that hole are x equals -1, y equals -1/2. Now, if you're feeling pretty comfortable with this, you could go ahead. This handout is available on my course webpage. You could go ahead and try the rest of these yourself. I'm going to keep working through them. So 2x squared minus 7x plus 6, we're going to have to factor that first. So it's going to multiply to positive 12. It's going to add to -7. And the two numbers that do that are -3 and -4. Then we take the leading coefficient of 2 and put each of them over 2. This one has to simplify to -2 over 1. The x's go with the denominator, or we read from bottom to top. So we end up, this first one is 2x minus 3, and then we have x minus 2, all divided by x minus 2. Now grab my highlighter because I want to show that those two are going to divide out, and leaving behind, put that back to yellow, leaving behind just 2x minus 3. So you can see at the end, we actually end up with, this is very much like what we did before. We've got a straight line here. We have a restriction on this, which is x is not allowed to be equal to 2. And I've got a y coordinate of -3. And I have a slope of 2. So that would be over 1 up 2, over 1 up 2, over 1 up 2, or left 1 down 2. That's as many as I can fit there. I'll put on my straight line, connecting those. And just extend this one a bit this way. Arrows on the end, but I do have, what is this? This was divided out, which means this is a whole. And so we are going to actually find the y coordinate of that by taking 2x minus 3, and we're actually going to put the 2 in there. So we end up with 4 minus 3, or 1. And that should be one that we can read. So that means the whole has coordinates 2, 1. And if we take a look, we could have gotten that from the graph. So there's a hole right there. Maybe I'll, let's see if I erase that and put in a nice clear open circle to represent the hole, which has coordinates 2, 1. Otherwise, it's a straight line. Okay, just a few more examples, just trying to show you the different scenarios and remind you, maybe in this case, different factoring techniques. X squared minus 9, that's a difference of squares. That's x minus 3 times x plus 3, all divided by common factor of 4. And then we end up with x plus 3, which means the x plus 3's are going to divide out. And our final form is, there's two ways to write this, x minus 3 over 4, or you might write this as 1/4 x minus 3, which is the same as 1/4 x minus 3/4. This actually ends up being pretty awkward to use in a slope-intercept form because you end up with this y-intercept of -3/4. So a couple of ways. The slope itself is easy enough to deal with. Actually, before we do that, let's just make sure at this point, we lost this information. So once you lose information, so I don't want to get sidetracked too much. Once you lose information, it's important that you start writing your restrictions. And if you simplify it further, I would probably like to see that those restrictions carry on, because what you're saying is this first line is the same as this second line, is the same as this third line, only where x is not equal to 3, or not equal to -3, is only equal to this when x is not -3, is only equal to this when x is not -3. So that said, if we take a look at this actual line, well, the line has a slope of 1/4, and that's easy enough to graph. We've got a nice grid to do that. But the y-intercept is equal to -3/4, and that's pretty awkward. So you might actually want to perhaps make use of the x-intercept. Just to go over here, how do we find the x-intercept? We set y equal to 0. And you're going to see that that actually ends up making this quite simple, because we have y equals x minus 3 over 4. We set y equal to 0 equals x minus 3 over 4. And then we end up with 0 equals x minus 3, or 3 is equal to x. So we end up with the x-intercept is just equal to 3, which is right there. And now from there, I can apply this slope. This slope is 1/4, which is basically saying that's rise over run. So that's up 1 to the right, 1, 2, 3, 4. I'm just going to extrapolate there. And then it would be down 1 and then to the left, 1, 2, 3, 4. Down 1 and to the left, 1, 2, 3, 4. And so being a little bit more flexible in our thinking allows us to graph a little bit more easily. And then from there, I just want to go back and double check my algebra. Whenever I have to do something unusual with this, it's always a good idea to check the algebra. X minus 3, x plus 3, divide out the 4. That's x plus 3, x minus 3 over 4. Yes, so I'm pretty confident with what I've got there. And so now from here, what I can do is identify where this hole is. So I know this hole is at x equals -3, so I can actually, let's choose a color that's going to stand out a little bit better. I know there's a hole there. What are the coordinates of that hole? In order to find the coordinates of the hole, I'm going to set x equal to -3. And I end up with y is equal to, is there any one of these that's easier than another to use? Not in particular. So y is equal to -3 minus 3 over 4, which is -6 over 4, which is -3 over 2. So the coordinates of this are -3 for the x, -3 over 2 for the y. And if we take a look, -3 over 2 for the y, or -1.5, that seems to line up pretty well with our graph. It's always good to have these things confirm themselves. And I believe that we are on the last example here. We are. So always thinking common factors first. Common factor between 4 and 10 is 2, giving me a 2x minus 5. And then I've got a difference of squares, 2x minus 5, 2x plus 5 for the difference of squares. And although you can usually count on the fact that something is going to divide out in these questions, you do have to be honest, make sure you're completing the algebra correctly, because you never know, it might not. So this one ends up being 2 over 2x plus 5. And we've lost information, but don't forget we still have a denominator here. So first of all, 2x plus 5. What makes 2x plus 5 equal to 0? I know that many of you can do this in your head. You end up with x equals negative 5 over 2, which of course means that we have a restriction there. X is not allowed to be negative 5 over 2. And that one is a vertical asymptote because it's still here. Then we also have a restriction from what got lost, and that was when 2x minus 5 is equal to 0, or x is equal to positive 5 over 2. And so we also have this restriction, x is not allowed to be equal to 5 over 2, and that represents a whole. So let's put on that vertical asymptote at negative 5 over 2, and we're going to just do our best. Negative 5 over 2 is the same as negative 2.5, so I end up with a vertical asymptote there. Now this one is going to be quite a bit more awkward as far as graphing. It almost makes me wish I didn't have this scaled graph here, because the point of this is not to have us worry too much about graphing. This one has some strange things in it. There's a k value here, there's an a value. I think for the sake of completeness, I'm just going to show you how I can put this into terms that we can actually maybe come to grips with a little bit more easily. So let me take that form y. Let's take that form y equals, you know what? I'm just going to just make myself some room under here by erasing this work. Okay. And now I'm actually going to leave the numerator alone, but I'm actually going to factor out that 2, leaving me x plus 5 over 2. It's not a big stretch what I'm doing here, but it might not occur to people to do it. And those 2's, of course, are going to divide out. Those 2's divide out and they just become equal to 1. So I end up with 1 over x plus 5 halves. And in each of these cases, my restriction is x is not allowed to be equal to plus or minus 5 over 2. X is not allowed to be plus or minus 5 over 2. But this is now, you can see by simplifying it, there are no stretches or compressions that I need to worry about. So with respect to these asymptotes, I'm only drawing the vertical one here. There's actually going to be a good point right there, and there's going to be a good point right there. 1 unit diagonally from where the two asymptotes meet each other. And then I'm going to just draw that in a reasonable way. It's never easy to draw the rational graphs. And now that I've done that, where is my whole? The asymptote is at negative 5 over 2, or negative 2.5. So we have a whole at x equals positive 5 over 2, which of course is the same as 2.5. So over here at 2.5, I have a whole. And what's the y coordinate of that whole? 2 over 2x plus 5 becomes 2 over 2 times 5 halves plus 5. The 2's divide out there, and you end up with 2 over 5 plus 5, which is 2 over 10, which is 1 over 5. So we end up with a whole having coordinates here of x coordinate of 5 halves, a y coordinate of 1/5. And that takes us to the end of our worksheet. Hopefully you took the time and worked through some of that sheet yourself.